Hello everyone. We are on chapter 4 about general vector spaces. Today we're going to be discussing section 4.4 on linear independence. And just taking a look back on our journey in chapter 4, 4.1 was about real vector spaces. And when we discuss real vector spaces, we're trying to verify that a particular set is a vector space by using our axioms 1 through 10. Then in section 4.2, we had to ask ourselves, can we verify a subspace within a vector space? And with that, we were verifying if a set was indeed a subspace with our axiom 1 and 6. And if we could verify axiom 1 and 6, then we knew that axiom 4 and 5 held true. And then we also knew that the rest of the axioms in 1 through 10 were inherited from the vector space V for the subspace W. And then in 4.3, we were looking at a set S, and then we were trying to determine a subspace W that was all the possible linear combinations of that set S. And so we would say that W was a subspace of the vector space V that was spanned by S, and we would kind of write it W equals span S. And then now, in our section 4.4, linear independence, we're once again going to be given a set S. And we have to determine if any of the vectors now in this set S can be expressed as linear combinations of the others. So that's where we're going today. So let's get into this in detail. So if we look at the objective of this section, in this section we will consider the question of whether the vectors in a given set are interrelated in the sense that one or more of them can be expressed as a linear combination of the others. So this is going to be important to know in applications because the existence of such relationships often signals that some kind of complication is likely to occur. So you are going to want to know whether they're interrelated and if they can be expressed as linear combinations of the others. So we have visited this concept before, but if you have a rectangular xy coordinate system, every vector in the plane can be expressed in exactly one way as a linear combination of the standard unit vector. So here we have standard unit vector I and standard unit vector j that are along the x and y axes. And so if we have this particular vector here represented by this point, we know that this point here can be expressed as 3 times the standard unit vector here along the x-axis, and then as well as 2 times the standard unit vector along the y-axis, or j here. And then we would further kind of simplify this and say this equals 3i plus 2j. So this is a very simple example where this vector here is represented here by its coordinate points. It can be expressed as a linear combination of our standard unit vectors in this manner. And so now we're going to look at the actual concept of linear independence. So here's our first definition of this section. Definition 1 says, if S is a set of vectors, v1, v2, all the way through vr. So if S is a set of 2 or more vectors in a vector space V, then S is said to be linearly independent set if no vector in S can be expressed as a linear combination of the others. A set that is not linearly independent is said to be linearly dependent. So here you have this set S of all these different vectors, v1 all the way up to vr, whatever however many there are. So that set is linearly independent if no vector in here is a linear combination of the others. So linearly independent set. Now keep in mind, just wanted to clarify here, S is a set in a vector space V. So you can confirm, so vector space V has been confirmed to be a vector space. However, I do want to draw your attention to the fact that S is just defined as a set here. It does not indicate that S itself is a subspace. So S is a set in vector space V, but it doesn't say if S is itself a subspace. It just says S is a set of 2 or more vectors. So there's at least 2 or more vectors. So these are going to be things that you want to make sure that you clarify with yourself. So if S has only one vector, we will agree that it is linearly independent if and only if that vector is non-zero. So just an example is, so if S includes the vector v1 equals 1, 1. Well, that vector in there, in that set S, is a non-zero vector. This is the only vector in that set, so you have to have at least, you know, 2 vectors in order to be able to kind of compare them and say, oh, one is a linear combination of the other or not. But since this only has 1 vector in that set, well, you can't really say there's another vector in there then that's a linear combination. So we would conclude that yes, this set of only 1 vector is linearly independent. And in general, though, I will say that the most efficient way to determine whether a set is linearly independent or not is to use theorem 4.4.1. So what is this theorem 4.4.1, you say? Well, here it is. It says a non-empty set S in a vector space V is linearly independent if and only if the only coefficient satisfying the vector equation k1v1 plus k2v2 plus however many vectors you have equals 0, and k1, k2 all the way through kr equals 0. Well, I do hope that you recognize what's happening here from your previous sections. And so basically what they're saying here is that vectors are linearly independent in that set S if and only if they satisfy. Hopefully you recognized that this is a homogeneous system. And they're linearly independent if k1, k2, all the way through kr equals 0. So basically you have only the trivial solution where everything equals 0. So they're basically linearly independent if they're satisfying this homogeneous system, and the only solution is the trivial solution. Okay? So hopefully you'll keep that in mind as we work through these problems. So let's look at example 1. Using our standard unit vectors. In this particular instance, we're going to be looking at these standard unit vectors in R3. Obviously, this will hold for whatever dimension you end up in. So we need to prove the linear independence between these standard unit vectors. So from that theorem I just showed you, we need to show that if we set these up as part of a homogeneous system here, so we have k1 times I plus k2 times j plus k3 times k, all of that is going to equal 0. And we will know that this is a linearly independent set of standard unit vectors if and only if k1 equals k2 equals k3 and all of those equal 0. So we only get the trivial solution for our unknowns k1, k2, k3. So I hope you will dig deep and go back to your previous chapters and sections. Remind yourself what is a homogeneous system. Remind yourself what is the trivial solution versus non-trivial solution. So here is where all of these concepts are going to play a part in what we're doing in chapter 4. So we would want to go ahead and set this up where all of this equals to 0, like I said. So we would have, basically we'd go ahead and put this in vector form, correct? So we'd have k1 times our vector standard unit vector I, so that'd be 1, 0, 0, plus k2, which would be 0, 1, 0 for our j. This is I, this is j. Here times k3 would be times 0, 0, 1 for our k up here, standard unit vector k, that is. And then we're going to have that set equal to 0, and in that, in component form, be 0, 0, 0. And so then we'd go ahead and solve this. So we'd have 1k1 plus 0k2 plus 0k3 equals 0. So I got that from, here's 1 times k1, so it went to this term. Then I have 0 times k2, be this term. We got 0 for the first component here, times k3, this term. We take the first component of the solution. So we're basically getting our homogeneous system of linear equations here. Using these standard unit vectors and the solution of 0. And so our next one is going to be 0k1 plus 1k2 plus 0k3 equals 0 for all our second components. Then we have one third equation here. We've got 0k1 plus 0k2 plus, now we have 1k3 equals 0. So I think it's pretty obvious from this first equation, guess what? K1 equals 0. From this second equation, we have K2 equals 0. And from this third one, K3 equals 0. And the only way that happens is if K1, K2, and K3 are all equal to 0. So we would, in this instance, be able to say, yes, indeed, that our standard unit vectors in R3 are indeed linearly independent. We have set them up in the homogeneous system equaling to 0, and then our values of K1, K2, K3, we only get the trivial solution. They all must equal 0 for all of this to hold true. So I hope that's a simple example showing how this works. Now we're going to actually look at some vectors that are not, of course, the standard unit vectors. In example 2, we have a situation where we're dealing in R3, and we're looking at whether the vectors v1, v2, v3 here are linearly independent or not in R3. So what do? We need to basically set up our homogeneous system here. So we've got K1 v1 plus K2 v2 plus K3 v3 equals 0. And now if we put in our specifics for v1, v2, v3, we're going to have our K1 times 1, negative 2, 3, plus K2 times 5, 6, negative 1, plus K3 times our v3, which is 3, 2, 1. And all of that is going to equal 0. So we'll put it in its 3 components form. And then we'll go ahead and create our system of linear equations for this that are all set to 0. So we have 1k1 plus 5k2 plus 3k3 equals 0. So that came from these first components, so 1k1 here, and then 5k2, and then we have 3k3 equals 0. All right, so we'll do our next set here. So we've got negative 2k1 plus 6k2, and then plus 2k3 equals 0. And then our last one is 3k1 minus 1k2 plus 1k3 equals 0. So with this one, you actually have a couple different options for solving this. Now remember, we need to figure out, okay, for setting these equal to 0, and then we're solving for our k1, k2, k3, do we get the situation where all of these equal 0 and we get only the trivial solution? Or do we not have that happen? Do we have it where, it's not, where K1, K2, or K3 doesn't just equal 0, that it could also have other solutions, so they have non-trivial solutions? So, or non-trivial solutions. So, hopefully you can see 2 different ways of possibly solving this. So one of them could be, and this is going to rely on your knowledge of your previous section. So one way that you could do it is if we're just looking at, kind of clear this out of the way here. So if we're just looking at these equations, well, maybe you think to yourself, well, you know what, I'm just going to simply use like back substitution here. So maybe if I start with this third equation down here, I say, okay, well, 3k1 equals k2 plus k3. Whoops, sorry, negative. And then what you could do, obviously you'd then divide each side by 3, but then you'd have at least a value here for k1. You could then go ahead and substitute those terms into your second equation. You'd be solving for either k2 or k3. Then you'd plug that into the first equation up here. And then you'd have basically, you'd see what you get for the solutions for k1, k2, and k3. So just to save time, I'll let you know that if you did use that method, you would get that k1 equals negative 1/2 t, and k2 equals negative 1/2 t, and k3 equals t. And so you will obviously notice here then that k1, k2, and k3 do not all equal 0, and that certainly k1 and k2 are dependent on whatever that value of k3 is. So we would say here that you have non-trivial solutions, because there's many different things that you could put in for k3. And so I hope that you do recognize that this would be a non-trivial solution, and that this is also written in terms of the general solution. So don't forget that concept. So the general solution, you could say that these are in terms of parametric equations using your parameters, where here we've assigned k3 as t, and then expressed k1 and k2 as in terms of t. The other thing is, don't forget that Your systems are either going to have 0, 1, or infinite many solutions. So don't forget about that either. All right, so let us go to, so that was method 1. So if you used, I'll just say here, back substitution, you left them as equations. But I will say that you could potentially do it another way. And I do want to draw your attention to the fact that you will want to make use of this theorem 2.3.8 for your work in chapter 4. You're going to be referring to it quite a bit. So you're going to want to remember this theorem, have it bookmarked. You're going to want to look through these equivalent statements because they're going to have some particular meanings for you in solving these problems. So for equivalent statements, they are either all true or they are all false. So that's the one great thing. So as soon as you're able to see one of these statements is true, well, then you can say, oh, well, the rest of them must be true, so I can make use of maybe another statement. That's going to help me solve these problems. So don't forget about that. So that would be method 2. And the reason that I bring that up is that you could have solved that system another way. You could have taken those equations that we had before. So see these equations right here? We would make use of those and we'd put them in terms of an augmented matrix. So we'd be able to say A equals, go ahead and put all these in here. Let's see, 1, 2, 3, and then you'd have 5, 6, -1, or 3, 2, 1. And you have this coefficient matrix of those equations. And you could use a couple different techniques here. Basically, you'd make use of this particular last statement. You would reduce this particular matrix and you would figure out the determinant. And then if you knew it was 0 or not, you would know whether or not it has only the trivial solution. So you could use these particular properties and you can make your conclusions there. So I will say for the sake of time though, you could do this in a couple ways. You could basically reduce this down and you would have an upper triangular matrices and you could calculate the determinant along the diagonal once you'd had reduced this. You could use the arrow technique to figure out the determinant of a 3 by 3 matrix. You could figure out the determinant that way. So like I said, you're going to make use of those techniques from your other sections. And so basically what you would come out with if you'd done that work, and you should do this to prove it to yourself, but you would come out with the fact that the determinant of A is in fact 0 for this particular matrix here. And so that would mean, okay, well, for AX equals 0 to have only the trivial solution, it means that its determinant A cannot equal 0. Well, if the determinant A here does in fact equal 0, then that means it's going to have non-trivial solutions. So you're making use of this theorem here with your equivalent statements to be able to figure this out. So here we would say, okay, well, determinant does equal 0. It means there are non-trivial solutions. And so what does this mean? It means that these set of vectors are linearly dependent. So I hope this is becoming clear how you're going to pull all these concepts together. Example 3 is very similar to what we just did, except it's in R4. You basically would set up your homogeneous system similarly. You'd use some different methods to solve for it, either by using your equations or manipulating a matrix. But I'm going to let you prove that for yourselves, but hopefully you want to go through that and see that they got for that example only the trivial solution. So in that instance, V1, V2, and V3 in this one, they are linearly independent. So for this one, you want to prove this to yourself that only the trivial solution. And so V1, V2, V3 are linearly independent. This brings us to our next concepts that are presented in Theorem 4.4.2. So these are also statements that contain useful information for solving problems. And Theorem 4.4.2 says that a set with finitely many vectors that contains the 0 vector is linearly dependent. So if you get a problem and it shows that it contains the 0 vector here, well then you know that set of finitely many vectors is going to be linearly dependent. In part B, it says a set with exactly 2 vectors, so that's important terminology here. It says exactly 2 vectors is linearly independent if and only if neither vector is a scalar multiple of the other. So if you have this set that just has 2 vectors and one of them's a scalar multiple of the other, well then they are not going to be linearly independent. So it can be linearly independent if and only if they are not a scalar multiple of one another. So let's go ahead and look at this in terms of our figures here that kind of really present this to us geometrically. So here we've got some figures here in R2 that I think you'll see how this works out. So this first one, these are linearly dependent because this vector here, 6, 2, is basically just going to be a scalar multiple of 3, 1. They're going to lie along this same line. But you have just a slight change where one is 3, 2 and the other one is 6, 2. These are now not scalar multiples of one another. So these are going to be linearly independent. We'll look at a couple other figures here so you can really see this. So here, these are in your textbook, this first set here. These are going to be 2 vectors in R2 or R3. So this one, V1 and V2, once again, both of them have their initial points at the origin. You can see here that V2 is just a scalar multiple of V1. It lies along this line that runs through the origin. So these are going to be linearly dependent. Keep in mind, we're talking about sets here of 2 vectors only. Here in this one, this is once again linearly dependent. V1 and V2 both have their initial points at the origin. They're both going to lie along the line through the origin. But here, this is going to be linearly dependent here as well because V2 just happens to be a negative scalar multiple of V1. They still both are on that same line. This third example here, though, these are linearly independent. Both of them have their initial points at the origin, but they do not lie here along the same line. So you would be able to say, yes, that they are linearly independent. Neither is a scalar multiple of the other. So looking in this in terms of R3, here you have, in this first image here on the left, these are going to be linearly dependent. U, W, and V are all linearly dependent because they are all vectors that have their initial points at the origin. They all lie in the same plane. Here on the right, these are actually linearly independent. You can see that U and V lie in the same plane. All 3 have their have their initial points at the origin, but you can see that this vector W does not lie in the same plane. So these would not be considered linearly dependent. They would in fact be linearly independent. And I have one more picture that's representing this. So here we have just another way to kind of visualize it. Here in A, V1, V2, V3, all of them have their initial point at the origin here. They're all lying in the same plane. Here's a different reiteration of it. Here we have V1, and then if you notice, within this same plane, V2 and V1 actually lie on the same line within that plane, so you could have that as well. These would be obviously linearly dependent. Here, C, though, here's another way to kind of visualize that these are linearly independent. They all have their initial points at the origin, but you can see this V1 does not lie on the same plane. So I really think that these figures help with visualizing this, so I encourage you to look these over. I have one more theorem that I wanted to introduce for this section, and that is theorem 4.4.3. And this says, let S be a set of vectors in Rn. If R is greater than n, then S is linearly dependent. Well, what does that mean? Well, if you notice carefully with the notation, you got S as a set of vectors, V1, V2, all the way through VR. So R is going to be your number of vectors that are in that set S. And here you have your real space, which goes out to the nth dimension. So what this is saying is that if you have more vectors in S, so you have R number of vectors in S, and if that's greater than your dimension, then S is going to be linearly dependent. So I hope that makes sense. So here is, if you have the number of vectors in S, if that's greater than your actual dimension number, then that means your set S is going to be linearly dependent. So you're going to want to review this one as well. In example 7, I just wanted to point out that you may in fact be dealing with matrices. So you want to remember that for your matrix, that your rows and your columns can be vectors themselves. So this example goes through and talks about the linear independence of row vectors in a row echelon form of a matrix. So you're going to want to check this out. So just remember that you can use this to apply to matrices as well.